So, good morning, everybody. Today we continue our discussion of the main laws of physics, elementary physics. And after discussing laws of kinematics, laws of uniform motion, and uniformly accelerated motion, we have to discuss laws of dynamics. Dynamics goes after kinematics, and dynamics means laws of Newtonian dynamics, because there are not only Newtonian dynamics in physics, there are other types of dynamics, but in the simplest and elementary level we study Newtonian laws of motion. It's absolutely clear that in just 3 or 4 months of this semester we will be unable to discuss all the laws of elementary physics, and also we will be unable to discuss any single law to a greater detail. So our course of introduction to physics is just a repetition of the most important laws. And the main purpose of this course is to learn how to solve problems in physics. And we will learn how to solve complicated problems, which may seem to be complicated to former school children, because I know that many school students in different countries have little practice in solving complicated problems, advanced complexity problems. So we will discuss physics laws shortly, and most of time will be devoted to solution of problems in physics. Today we will repeat laws of Newtonian mechanics, Newtonian dynamics. There are 3 laws, 3 laws of Newtonian dynamics, and the first Newton's law says a body at rest will remain at rest unless acted upon by an external force. So a body at rest will remain at rest unless acted upon by external forces. We will discuss this law in some detail later, and now the second Newton's law, you know very well that acceleration of a body is directly proportional to the force acting on this body and inversely proportional to the mass of the body. And also, certainly acceleration is a vector, and the force is also a vector in this equation. And the third Newton's law says that any action is always accompanied by reaction. Any action, any force of action is always accompanied by a force of reaction, so that the force acting from the first body on the second body is equal to minus vector of force acting from the second body on the first body. If we have 2 different bodies, the body m1 of mass m1 and another body of different mass m2, and these 2 bodies interact due to any physical mechanism of interaction. It may be electrostatic interaction, it may be magnetic interaction between 2 magnets, it may be gravitational interaction, it may be any kind of interaction. For example, it may be simply a spring. A spring may be here, And if the spring is compressed, then the spring will act on each body. The spring will act here, that is from the force from body 1 on body 2. And also there will be the force acting on another body, the force from body 2 on body 1. And these two forces obey the second Newton's law, third Newton's law. The force of action equals and is equal and oppositely directed to the force of reaction. So these three Newton's laws lay the foundation of classical mechanics. And now we will discuss shortly each law. What does it mean that the body is at rest? How do we understand it? It doesn't move. If it's at rest, its velocity is 0. And also its acceleration is 0 because the body remains at rest. It doesn't start moving, so acceleration is 0. Well, if you look at the second Newton's law, you can easily understand that the acceleration will be 0 if force is 0. So, if there are no forces, then acceleration is 0. It seems to be the same as the first law. The first law seems, at first sight, seems to be a consequence of the second law. At first sight, it seems to be that the first law follows from the second law, but that is not absolutely true. No. The first law is a separate law. It has very important meaning in itself. Why so? Because, think about it, if the body is at rest, how can we measure the state of rest of the body? How can we make sure that its velocity remains 0? Only by introducing coordinates, a coordinate system, a reference system. So in order to be sure that the body is at rest, we have first to introduce some reference frame and coordinate system associated with this reference frame. So the reference frame is most frequently 3 axes in our three-dimensional space, x, y, z. And in this reference frame, some material point has its own coordinate. The coordinates will be the x coordinate and y coordinate, and also, if you put it in this way, there will be a z coordinate. I'm not very smart in drawing pictures, but you know that this point may not belong to the xy plane. It may be here in space, and then it will have its z coordinate. Well, so in order to formulate the first Newton's law, we must introduce the reference frame and the coordinate system associated with this reference frame. Actually, in physics, reference frame is actually a solid body with some solid rods attached to it and with unit lengths shown on along each rod. Each rod will be an axis, x or y or z axis. So this is, in order to materialize this reference frame in physics, we have to place a solid rod here along x-axis. And the solid rod should have units of length, like 1 meter, 2 meters, 3 meters, etc., in order to measure length, in order to measure distance. And then, if we have such rods, which are attached to some solid body here, then we have a reference frame, we have coordinate system, which can be used for measuring. So that should be some real material reference frame, not merely an abstract line in space. It should be some method of measurement. The coordinate system in physics implies there is a method to measure the distance, and method to measure the displacement of a material point. So if the material point remains at rest in some reference frame, in some coordinate system, then it means that there is such a reference frame which has this property. The property, such property that this body remains at rest if there are no forces, no external forces acting on it. If no external forces, if all the external forces are equal to 0, then the body remains at rest. Where? It's not an abstract body hanging in a free space, empty space. No. There is some coordinate system which possesses this property. So such reference frame or such coordinate system is called an inertial system. Inertial coordinate system. Inertial. R here should be inserted. Okay, so the first law of Newton, the first Newton's law says that there is at least one inertial reference frame in our universe. There exists at least one such reference frame that a body will remain at rest if there are no external forces. That is the reason behind the first Newton's law. It says there is at least one inertial reference frame in our world. Let's consider a different reference frame. Let it be x prime, y prime, z prime. Different reference frame which moves at some velocity v with respect to the first reference frame. Then, if you look at this material point from the second reference frame, you will see that this point is not at rest. It keeps moving because this reference frame moves. So with respect to the second reference frame, the material point will have some velocity, minus v actually. And this velocity will be constant. It will not change if there are no forces acting on the body. So, if there is at least one inertial reference frame in our world, then a body at rest with respect to this inertial reference frame will remain at rest unless acted upon by external forces. But at the same time, any reference frame which moves will possess another property, that the body, if no forces act on the body, then its velocity will remain constant. If no forces act on the body, then the velocity of this body will remain constant with respect to the second reference frame. And such reference frame also called inertial reference frame or inertial reference system. Inertial, let me put it in correct. So if there is a single inertial reference frame in the universe, then there should be many inertial systems, all of them moving at constant velocity with respect to the first inertial reference frame. So actually what the first Newton's law says, if we put it to include the velocity of the body, if we say that the body will remain at rest or in a state of uniform motion unless acted upon by other forces, if we add the velocity, if we say uniform motion, motion with constant velocity, then we say actually by saying this we mean that there is at least one inertial reference frame in the universe. And if there is one inertial reference frame, then there is an infinite number of other reference frames possessing the same quality, infinite number of other inertial reference systems. That is the meaning of the first Newton's law. It says that our world is such that there exists at least a single inertial reference frame which possesses this quality. By the way, is this law absolutely correct? Can you show me actually an inertial reference frame in our world? Is our planet an inertial reference frame? No, because the planet is rotating. With rotation, any acceleration is inevitable for any material point, unless it's acted upon by external forces. If we take a body in outer space which is free of any action, nothing is acting in it, then the body will be accelerated with respect to the Earth because the Earth is rotating. So the Earth cannot be considered, strictly speaking, the Earth is not an inertial reference frame. Well, our Sun or other distant stars, can they be used to construct somehow an inertial reference frame in the space? No, because all the stars move in the galaxy in complicated orbit, elliptical orbit, close to elliptical, around the center of the galaxy. So no stars, no system of distant stars can be considered an inertial reference frame, strictly speaking. Okay. If we keep on discussing this situation, we will discover that actually there are no inertial reference frame in our universe. No single reference system can be considered an inertial, strictly speaking. Only approximately, only with some degree of approximation and a reference frame associated with the planet Earth can be considered an inertial reference frame. It's an approximate law. But the approximation sometimes is very good. For many purposes, the Earth can be considered an inertial reference frame. The approximation is good. An error which will be caused by non-inertial properties, by the rotation of the planet, will be small. In many situations, the error, the discrepancy will be small. So the Earth can be considered as an inertial reference frame to such degree of approximation. It's not strictly, it's not an absolutely inertial, no, it's not inertial, but approximately. In many problems, it can be considered as an inertial reference frame. Also, distant stars or lines to the distant stars from our Sun can be considered as axes of an inertial reference frame to some approximation, to some degree of accuracy. And the degree of accuracy, well, is very good. It's very high degree of accuracy. But anyway, this is not an inertial reference frame in the strict sense of the word. Strictly speaking, there is no single inertial reference frame in the universe. But approximately, with some degree of approximation, yes, there are some inertial reference frames in the universe. For example, our planet, for example, distant stars, etc. So this law says that there is at least one inertial reference frame in the universe, but we understand that there are none, and only to some degree of approximation this law can be accepted. But the degree of approximation is very good in many situations. As far as the second Newton's law is concerned, how can we use it if we don't know what is acceleration? But you know what is acceleration. You know that by definition, acceleration is the change of velocity vector divided by the time interval during which this change in velocity took place. So this is a definition of this quantity, acceleration. So if we have defined this property in such a way that we can measure it. We can measure acceleration using the measurement of velocity and time intervals. If we can measure acceleration, if we can calculate it, then we can use this quantity in some equation. Now we have to define what is force. If we don't define, if we don't have any method of measurement, then this equation will become useless. How can you use this equation if you don't know what is this? What does this letter stand for? What is it? How can you measure? How can you measure forces? If you don't know how to measure force, you are unable to use this equation. So, forces can be measured in different ways. For example, using a dynamometer, which is based on a spring. So if we have a unit mass body and a spring of some stiffness K, and the unit mass body of 1 kilogram mass is attached here, then the spring will elongate. So this is a natural length of the spring, and this is an elongated length. That's an elongated length. So by elongation of the spring, you can measure the mass of the body which is attached here. If you attach 1 kilogram body, then the spring will be elongated by some distance. But if you attached here a body of an unknown mass, then the elongation of the spring will be different, but it will always be related to the weight of the body. And the weight of the body is known to be the mass times acceleration of free fall. So the weight of the body, which is the force acting on the body, can be measured using the spring. Such a simple device. So forces can be measured by different, actually there are many methods to measure force, but the simplest method is this one. And forces can be measured. And because forces can be measured by comparing any force to a force acting on a unit mass body, by comparison, anything can always be measured by comparison with the unit of measurement. The length can be measured, or distance can be measured if you compare the distance with the unit of length, with 1 meter distance. So there should be a unit of force. A unit of force is 1 Newton, which can be derived from here. Force. If we consider the unit of measurement of force, I would denote it in this way. This is not a force. This is a unit of measurement of force. Then the unit of measurement of force will be the unit of measurement of acceleration times the unit of measurement of mass. And that will be, mass is measured in kilograms, and acceleration is measured in meters per second squared. So this unit of measurement is known as a Newton. This is a Newton. So as far as units of measurements are concerned, if we have a unit of measurement which is named after some person, after Newton or other persons, then the unit of measurement is denoted by a capital letter, capital N. But if the unit of measurement is not based on somebody's name, like meter, second, it's not the name of a person, then small characters are used. Small m and small s, if it's not a name or surname of a scientist. But if you have a name of the scientist in the unit of measurement, then the unit is used in capital letter. So 1 Newton is 1 kilogram times 1 meter over second squared. That is the unit of measurement of force. And actually comparing any force with unit, you can measure any force. And if you have a method to measure a force, then you can use this equation. Also, you have to know the method to measure mass. We discussed it last time, how to measure mass, again, comparing it with other masses. So this law can be used if you know exactly how to measure acceleration and how to measure forces and how to measure masses. And measuring forces can be reduced to calculation of forces in many situations. For example, if you have two electric charges, one electric charge plus Q1 and another electric charge plus Q2, and the distance between them is R, then the force of action between these two, electrostatic interaction between these two charges, will be given by Coulomb's law. Q1, it will be proportional to Q1, Q2, and R squared, with probably some coefficient of proportionality which depends on the units of measurement. We will discuss it later when we will consider electrostatics. But I would just like to remind you that sometimes you don't need to measure force, you can calculate it. You can calculate forces if you know the formula for a particular force in a particular situation. For example, in electrostatic interaction or in gravitational interaction also. If you know the formula, you can calculate the force. You don't have to measure it every time. But anyway, there should be a method of measurement in order to use this. Okay, now, is this law always correct? No. Just like any other law in physics, this law is not always correct. It will have some different meaning in relativistic physics. Actually, in relativistic physics, it's not convenient to introduce forces. Forces are not considered in relativistic physics. So this law will have some different meaning. There will be not forces, but momenta of bodies. And also this law is broken in quantum physics. In quantum physics, it's impossible to introduce a coordinate of a particle. It's impossible to introduce a certain trajectory of a particle motion. And it's impossible to introduce an acceleration. In general case, for example, for particles moving inside the atom or inside the molecule, it's impossible to use the Newton's law because laws are different there. Laws are different in relativistic physics and in quantum physics. This law will not be true. Now, as far as the third Newton's law, it seems to be always true. It seems to be always correct. The force of action should be equal and oppositely directed to the force of counteraction. But again, this law is not always correct. It's not always correct because, well, we will discuss it in greater detail in the second semester. In the second semester, we will discuss in greater detail why this law is not always correct. Sometimes it's approximate. Now, I will not waste my time on this discussion because we will discuss it later in February next year. And now I would like to consider some problems based on Newton's laws. After discussing the Newton's laws, we will discuss the solution of problems. Certainly, we will use Buchovtsev's collection of problems in physics. And the problem I would like to discuss will be number 41. Well, very, very simple problem. Number 41. Number 41 from Buchovtsev's collection of problems. 6 forces lying in one plane or belonging to one plane and forming angles of 60 degrees relative to one another are applied to the center of a homogeneous sphere with a mass of 4 kilograms. So the mass of the sphere is given 4 kilograms. These forces are consecutively equal to 1, 2, 3, 4, 5, and 6 kilogram forces. In what direction and with what acceleration will the sphere move? So we have a sphere. I will not try to draw a sphere, but what is important, we have forces, 6 forces. Force 1, and at 60 degrees, force 2, and again at 60 degrees, force 3, and here force 4, and 5, and the strongest force 6. The magnitudes of these forces are given. Force 1 is 1 kilogram force, this is 2, this is 3, this is 4, and this is 5, and this is 6. The units mentioned here are kilogram forces. What is kilogram force? A kilogram is the unit to measure mass. The force is the unit to measure force. But what is this strange unit kilogram force, which you will see in this collection of problems by Bukovtsov? To some unknown reason, Bukovtsov is very fond of this unit of force, kilogram force. So what is it? What is 1 kilogram force? If you take a mass of 1 kilogram and you put it on a horizontal surface, then there will be a force acting from this mass on the surface, and the force will be equal to mg. It will be equal to 1 kilogram, this is the mass of the body, times g, the acceleration of free fall, 9.8 meters per second squared. So this is the mass of the body, and this is the acceleration of free fall. This figure 9.8 is approximate. In every point of the Earth's surface, the accelerations are different in different points, but they differ in hundredths in the second place after the decimal point. So somewhere the acceleration may be 9.81, in other place on the surface of the planet the acceleration may be 9.82, in other places it will be 9.815. So acceleration is different in different places, but approximately it's just like 9.8. And in most cases it can be calculated as 10, meters per second squared. In many situations we just take the acceleration of free fall as equal to 10 meters per second squared. So if we take into account these figures, we obtain 9.8 kilograms per meter per second by meter per second squared. That is Newton. 9.8 newtons. And that force is denoted by 1 kilogram force, by 1 kilogram force. That's it. By 1 kilo, that is 1 kilogram force. Such a non-system unit to measure forces. That is the force which is exerted by a mass of 1 kilogram on a horizontal surface. If the surface is at rest, then the force will be 1 kilogram force. Such is the unit used in this collection of problems by Bukovtsov. So we have 6 forces, all acting in different directions, and the angle here is 60 degrees everywhere, 60 degrees here and here and here, everywhere 60 degrees, and we have to calculate the acceleration of this mass. We have to find the acceleration. This is the mass. Here is the mass m, and we have to find the acceleration of this mass. We have to find the acceleration. Does it work? So, to find acceleration, we must use the second Newton's law. Acceleration as a vector. Well, what happens to it? I don't know. It doesn't work. Acceleration as a vector is the force vector of total force divided by m. 5 minutes interval. Okay? So you know what is a kilogram force. What does it mean? This strange unit. This is just 9.8 newtons. So in order to solve this problem, we have to find the net force acting on the body. The body is here, and it has the mass of 4 kilograms. And in order to find acceleration of the body, we have first to find the net force. What is the net force? That is the vector sum of all forces acting on the body. The vector sum. So in order to find the net force, we have to add all the forces. F1 plus F2, etc. plus F3 plus F4, etc. We have find the vector sum of all the forces acting on the body. In this particular case, this can be easily done. For example, if we consider forces acting upon vertical direction, there will be only 2 forces, F1 and F4. And these 2 forces have different directions. So the total force acting in vertical direction will be directed downward because the force F4 is larger, and the force acting in vertical direction will be directed downward, and it will be equal in magnitude 4 minus 1, that is 3. F4 minus F1. In magnitude, 4 minus 1 is 3. And in direction, this force will be directed downward. So that will be equal to 3 kilogram forces. Then let's consider forces acting along this direction at 60, which is at 60 degrees to the vertical. Along this direction, there are 2 forces acting along this direction, F2 and F5. And again, F5 is larger, so the net force in this direction will be looking here. I will show the direction of the net force here acting in this direction. And in magnitude, it will be equal 5 minus 2, which is again 3. So we have taken into account vertical direction, and we have taken into account this inclined direction, and the only direction remaining is this one. It's taken into account, and again, this force F6 is larger than F3, so the sum of these 2 forces will look into this direction of F6, and in magnitude it will be equal to 6 minus 3, which is again 3 kilogram forces. So instead of 6 forces, we now have the system of 3 forces. We have reduced the number of forces by a factor of 2. All these angles are 60 degrees. 60 degrees. So instead of 6 forces, we have 3. we may forget about the 6 forces. And now we work only with these 3 forces, which are totally equivalent to the original 6 forces. This system of 3 forces is equivalent to the original system of 6 forces. So we replace the original system of forces by a new system of forces, which is much simpler because the number of forces is smaller. Now we have to calculate the net force using these 3 forces. Well, if you draw this picture correctly, which is not the case here, let me do it better. This is the force 3, and another force better shown in this direction, which is, this is 60 degrees. If you draw a perpendicular line from the end of this vector to the direction of another vector, then if this line is perpendicular, then this is the right angle, and that will be the right triangle. And so in this right triangle, the length of this leg will be half the length of this side, because it will be half the length, because the length of this leg, well, let it be A, and the length of this will be C. Then A divided by C, by definition, is cosine of this angle 60 degrees. And cosine is just 0.5 of 60 degrees. So A turns out to be C divided by 2, because we know this, the value of this trigonometric function, cosine of 60 degrees equals to sine of 30 degrees. This is the angle of 30 degrees. And the sine of 30 degrees will be 1/2. So we can easily calculate the length of this leg. It will be half the length of this side, which is 3. So this will be 3/2. That means that the component of force, well, let me denote it somehow. I will have new notation. This will be force 1, and that will be force 2, and that will be force 3. So force 1 will have 2 different components. One component perpendicular to force 2, and another component parallel to force 2. Also, force 3 will have 2 components, one component perpendicular to force 2 and another component parallel to force 2. As these angles are the same, they are equal to 60 degrees, both angles are 60 degrees, and both forces F1 and F3 have equal magnitude. For this reason, the components of these 2 forces, F1 and F3, perpendicular to direction of force F2, are equal. The component of this force perpendicular to direction 3, that is perpendicular direction, and the component of another force perpendicular to the direction 3. These 2 components are equal, and they will balance each other. We don't have to take them into account, the perpendicular components. I mean perpendicular to direction of force F. So we must take into account only the components of these 2 forces which are directed along F2, along this direction. And these components are easily calculated from geometrical point of view. This is the component of force F1 in the direction of force F2. And this component turns out to be just half the magnitude of force F1. And the same will be true for the force F3. Another component of force F3 looking along force F2 will be the same. So the total force acting along the force F2 will consist of two components, component of force F1 plus component, the same component of force F3. And both components are equal in magnitude. So their length will be 3. Let me put it this way. The force F1, a component parallel to force F2, that is the component of F1 on the direction of F2. We have found it, it's 3/2, and it's equal to the component of force F3, again on the direction of force F2. These are two equal components, and therefore the total force acting in the direction of F2, the total force will be F2 itself plus the two components of two other forces which we have calculated. Each component at 3/2, so the sum of two components will be 3, and the force F2 itself is 3. So the total force acting in this direction, let me denote it by F. That will be F2 plus all the components which are written here, that is plus 3, and that will be equal to 6. That is the net force acting on the body M. And if we know the net force, then we calculate the acceleration, which will be the net force over M. Net force is found to be 6 kilogram forces, which is 6 times 9.8 newtons. Finally, we have to use the international system, the SI system, and the units of force are newtons. So this is 1 kilogram force, 1 kilogram force in newtons, 9.8 newtons. And we have found the net force acting on the body to be 6 kilogram forces. So this is this number of newtons divided by 4, which is the mass of the body, divided by 4 kilograms. Now, approximately this is 10 times 6, 60 divided by 4, 15 approximately meters per second squared. So we have found the acceleration, we have found the answer to the problem. It was required to find the acceleration of the sphere M. And in order to find the acceleration, we had to find the net force acting on the sphere, that is the vector sum of all forces. And we have found the vector sum to be equal to 6 kilogram forces, which is approximately 60 newtons. That's very simple. The only difficult step in this problem is to find the direction of acceleration, which will coincide with the direction of force number 5. So the vector of acceleration of the sphere will have this direction coinciding with the direction of force number 5 in this problem. And then, using simple geometrical considerations, we find the magnitude of this force, which consists of components of several other forces. Nothing more than geometry. Well, do you know what is cosine? Tell me, please. Do you know? Huh? Cosine. And what is sine? You know how to work with these geometrical functions. That's okay. We will use it very often. Very often. Hmm? Oh, that's good. We can switch between different screens, between different windows. So there is a new window for another problem. Any questions regarding this problem? Any questions? Do you understand how to find a net force? Just to find a vector sum of all forces. A vector summation of all forces. That's what you need to do. Okay, and then to use second Newton's law. One of the simplest problems, and another one will be probably Oh, let it be this one. Number 53. Let it be number 53. A weight G is attached to the axis of a moving pulley. So we need to reproduce the figure. So there is a string which goes around the moving pulley, and to the axis of this moving pulley the weight G is attached, and the string goes further around another pulley which is fixed here, and here we pull with some force F. So a weight G is attached to the axis of a moving pulley. So this is the axis of a moving pulley. It can move if you push. If you pull this string, then this pulley will rotate and move up or down if you move the end of the string. What force F should be applied to the end of the string? What force F, we need to find it, should be applied to the end of the string here, which passes around the second pulley, so that the weight G moves upward with an acceleration of A. So we are given acceleration, and the weight G should move upward with acceleration A. This is the first question. So the weight of this body is given, and we want it to move upward with acceleration A. Acceleration A is also given, and we need to find the force. This is the first question. We need to find which force in magnitude, what should be the magnitude of this force applied to the end of this string, so that the weight G moves upward with acceleration A. This is the first question. And there is another question which we will consider later. So let's consider this problem. In such problems, it's always assumed that the mass of the pulley is negligible. And also the mass of this pulley is negligible. We may say that the mass is 0. We understand it's not 0, some very small mass, but it can be neglected in this problem. Also, we consider such pulleys which have zero friction in the axis. So there is no friction, the pulley may rotate freely without friction, and the mass of the pulley is zero. And also the mass of the string is zero or negligibly small. In such problems, it's always the case that we consider negligibly small mass of the string, negligibly small mass of the pulley, and no friction or practically no friction, negligible friction at the axis of each pulley. In this case, what happens? If this weight goes up with acceleration a, then there should be some force acting on this weight upward. Also, there is a force of gravitational attraction. The force of gravitational attraction is given to us. It's the weight of the body, which is always equal to mg, the mass of the body times acceleration of free fall. And there is another force, let it be T, the force of tension in this string. So this body moves with acceleration. It means that we have to apply the second Newton's law, because the second Newton's law defines the acceleration of the body. In order to solve this problem, we have to use the second Newton's law, which says that the mass of the body, this mass, times its acceleration should equal to the vector sum of all the forces acting on this body. How to find all the forces acting on this mass? We have to recall that a force is always a measure of interaction. If there is an interaction with outside bodies, then there is a force. If there is no interaction, then the force is zero. So this mass m interacts with some external bodies. Which bodies? Only two bodies. First, this mass interacts with the planet Earth, with this force, gravity, attraction. And second, this mass interacts with this string. And the force of interaction is denoted by T, which is the force of tension in the string. So there are two forces acting on this body. Only two forces, because only two interactions are involved in this particular problem. In other problems, there may be much more, many more forces and interactions, like in previous problem. So only two forces acting here, and if we assume that the direction upward is positive, then all the vectors looking upward will be positive, and all the vectors looking in opposite direction will be negative. So the force of tension T will be positive, and the force of weight G will be negative in this equation, because these two forces have opposite directions, and the direction upward is taken to be positive. We assume it to be positive. We can certainly assume different direction to be positive. Then all the vectors directed downward would be positive, and all the vectors directed upward would be negative. Negative minus sign will be here, and minus sign here, and here will be plus sign. Nothing will change. The same equation. So it doesn't matter which direction you choose as a positive direction. It doesn't matter. The final result will not depend on this choice of positive direction. Final result will be the same. So any direction can be chosen as positive, just for convenience. Just whichever direction you believe is convenient to choose as positive. So this is the equation of motion of mass m. This is the second Newton's law. in order to find the acceleration, acceleration is given, and the mass is also given because g is given. So we need to find force F in this problem. Everything here is moving with acceleration. The weight g moves upward with acceleration, and therefore this pulley moves upward with acceleration, and the rope is also moving with acceleration, and this pulley is rotating with acceleration. So the mechanical system is complicated. But if all the masses of pulleys are zero, or accepted to be zero, and the mass of the rope and the mass of the string is also zero, then we don't have to take into account this motion, accelerated motion of pulleys and the string. We don't have to take it into account because the influence of masses of the string and masses of the pulley is negligible. The influence is very, very small. We can neglect it. You don't have to take it into account. Therefore, force F acting here at this point will be the same as the force F acting here at this point of the string. And it will be the same as force acting at this point of the string. You can break the string here and insert, you can break it here and insert a small spring dynamometer here, and so you will have the possibility to measure force of tension in this point using the spring. And you can use this spring to measure the force of tension at any point along the string. And as the string has no mass, then this any element of the string delta m times acceleration of this string, but I don't know what is it, I will call it A prime, will be equal to the difference of two forces of tension here, T1 minus T2. For example, this is T1 at this point and this is T2 at this point. But as the acceleration is non-zero, because we know everything is accelerating with given acceleration, it's large. But as delta m tends to zero, it's given to us that we have to neglect the mass of the string. As this is zero, then we conclude that T1 is approximately equal to T2. Forces of tension here and here at different points are the same. Therefore, the force of tension along the string is the same everywhere. And if the force of friction is, if the force of tension is F equals to F at this point, then it will be equal to F at this point. And also it will be equal to F at this point. The force of tension is the same along the string because the mass of the string is negligible, practically zero. And from this Newton's equation, second law, we conclude that if the mass of the section of the string is very small, then these two forces are practically the same, practically equal. So the force of tension is the same everywhere along the string, and we have two forces of friction, two forces of tension of the string tension acting here on the pulley. Therefore, the mass of the pulley, let it be mu, times acceleration of the pulley, will be defined according to the Newton's second law by the total net force acting on the pulley, which is upward acting two forces F plus F, F from here and F from here, two forces F, and downward we have a force of tension T, which is the same everywhere along this string and here. So downward will be force T. That is the second Newton's law as applied to the center, as applied to the motion of the center of mass of this pulley. Two forces F acting upward, minus one force of string tension T acting downward. The total force will be given by this expression, so that will be equal to the mass of pulley mu times acceleration of the center of mass of the pulley. That is the second Newton's law. But we know that the mass of the pulley is practically zero. That is zero. We assume it to be negligible. If it was not zero, we should have used this equation. But in this problem, it's given that the mass of the pulley is zero. So, therefore, from here we conclude that the two forces F are equal to T. And so, we know what is T. T is the force of tension in this string. And it's equal to 2F. And we can substitute this magnitude in this expression and put it in this way. 2F, which is the force E, minus G. And we know that G is related to the mass of the body. So the mass of the body is not given in this problem. We have only two values given in the two quantities given in the statement of the problem, G and A. We don't know mass. And so the mass should not enter into the final answer. The mass should not be found in the final answer to this problem. It's not given. So we have to express the mass using the quantities given in the problem, that is capital G divided by small g, by acceleration of free fall. And using this notation here in this expression, we find that mass is capital G over small g, and it should be equal to, well, times acceleration. I have almost forgotten about it. Times acceleration. It should be equal to 2F minus G. And what do we have to find in this problem? We have to find the force F, which is required by the statement of the problem. So we can find force F from this equation. All other quantities are given or supposed to be known, like the acceleration of free fall. It's not given in the problem, but we believe it's well known in any problem. We know acceleration of free fall. So we can find F from this equation. It will be what? To solve this equation, we will take this expression divided by 2. That will be A capital G divided by small g plus G. That may be considered to be the answer, the final answer to the problem. We have to find force F. We have to find this force with which we must pull the end of the string so that the body, the given body, have the acceleration A upward. We have found this force. That's it. We can put it as capital G divided by 2 A plus small g divided by G. Simple algebraic transformation. We take capital G here divided by 2, and in the brackets, in the round brackets, you will have A plus acceleration of free fall G divided by G. That's it. That's it. We have found the final answer. Why do we know that this is the final answer? The first indication is that every quantity in this formula is given and is known. It's given in the statement of the problem. That is the statement of the problem. Everything is given. The weight of the body G, the acceleration A with which the body moves upward, and the acceleration of free fall certainly is known. So this formula contains only the quantities given in the problem. So it may be considered as a final answer. Also, it's always very useful to check the final answer for units of measurement. The units of measurement should be that of force. We need to find force. So the final formula should give us the units of measurement of force. Does it give us the units of measurement of force? G is force. And here we have acceleration in the numerator and acceleration in denominator. The units of acceleration will cancel, and the only units remaining here, the units of measurement, will be the units of force. That's it. Units of measurement are correct. We needed forces. We needed to obtain force, and we actually obtained force. This is a good example how to find mistakes in your solution, by the way. You could have made a mistake somewhere. For example, we could have missed something. We could have missed this character. And we could have obtained g over 2a plus g, for example. We could have missed this one. No. We could have missed this quantity. And then we could have obtained such an answer. It looks good. But the units of measurement of this formula will be wrong. It will be force times acceleration, which is wrong. We need only force. We don't need force times acceleration. We need only force, which is measured in newtons. And here we will have newtons times meters per second squared. That will be wrong. That formula will be wrong because units of measurement do not fit the required quantity of force. That's it. So we check, first of all, when we obtain the final answer to any problem which you will solve here, more than 100 problems. More than 100 problems in this collection of problems that are included in your home assignment for this semester. So more than 100 problems, and you will obtain answers to every problem, and you must check the answer always. First of all, look into the quantities contained in your answer, in your final formula. All the quantities should be known. If any quantity is unknown, then this is not the answer. The answer, final answer to the problem, should contain only the known quantities, only the quantities which are given in the problem statement. Then the second step is to check the units of measurement. The units should be correct. And then there is another step. There is another criterion of correctness, correct answer. Another criterion is a physical sense, I should say. So, for example, it's quite obvious that the greater the acceleration of this body, the larger should be the force. That's obvious. Does this formula provide this dependence? The larger the force, the larger the acceleration. And the larger the acceleration, the larger the force. Yes, it seems to be correct. The dependence of force on acceleration seems to be correct. The larger the acceleration, the larger should be the force. Yes, that's the case. That's what this formula gives. That's it. Okay. Any questions? No questions as far as this problem is concerned. Everything's clear. Okay, let's consider another thing. I would like to consider a body on the slope. So we have a slope, an inclined surface, which is at angle alpha to the horizontal. And there is a body. here, which can slide down, and we need to find acceleration A with which this body M slides down. Seems to be very simple, but it's not as simple as it may seem. So, in order to find acceleration, we have to use the second Newton's law again and again. Acceleration is proportional to the net force and inversely proportional to the mass of the body. So, in order to find acceleration, we have to find the net force, which is the vector sum of all forces acting on this body. In order to find forces, we have to consider all the interactions between this body and outside world. All the interactions. So, this body interacts with which other bodies surrounding it? This body interacts only with two bodies. The block on the surface interacts with the planet Earth. This is the gravitational pull. And also this body interacts with the surface. No other interactions. So only two forces. The first force is from the Earth and another force is from the surface. If we don't consider friction for the beginning, then the force of interaction with the surface will be perpendicular to the surface. Because there are no friction. A friction force is applied parallel to the surface. But if friction is zero, then no parallel component should be in this force of interaction between the given block and the surface. If no friction, then no component directed along the surface, no force component. The only force component here will be perpendicular to the surface. What will be the vector sum of these two forces? So this is the vector and this is also the vector. What will be the direction of the vector sum of these two forces? We know the direction even without solving the problem. We don't have to solve the problem in order to find the direction of the net force acting on this block. We know the direction because the acceleration of this block may be directed only along the surface. The block is unable to jump from the surface and is unable to break the surface and go through it. So its motion should be directed along the surface and the acceleration should be directed along the surface, and therefore the force, net force, should be directed here. That will be the direction of the net force. And so if we know the direction of the net force, then we can easily calculate it. The net force will be denoted by R, and R in magnitude, in R, vector R directed parallel to the surface, and in magnitude it will be, if this is alpha, then this is alpha also, and R in magnitude will be mg sine alpha. And so in this case, that will be the net force magnitude acting on the block. And the acceleration in magnitude will be F divided by m. After dividing by m, we will find g sine alpha. Very simple. G sine alpha. Very simple until we don't consider forces of friction. Now let's consider the possibility of friction. And if there is any friction, then there should be a force of friction. Let it be small f. A force of friction. A force of friction is always related to the force of normal action n. There is a coefficient of friction here. There is always such a dependence between the force of friction and the force of normal action. The force of interaction between the block and the surface, normal interaction. Why so? You should always be able to answer this question, why? In any situation, for any formula. Why so? Very simple. This is the definition of the coefficient of friction. This is just the definition. What is coefficient of friction? It's such a coefficient which relates in this way the force of normal interaction between the block and the surface and the force of friction. So, how to answer the question why this formula is correct? Because this is the definition of the coefficient of friction. So, what is n in this formula? N can be calculated because the normal to the surface component of the weight, mg, which is mg cosine alpha, the normal component of the weight of the body, should be equal to this normal force of interaction between the body and the surface. Why these two forces should be equal? Because the body does not move in this direction. The body moves only along the surface. It does not move in perpendicular direction. It cannot break the surface and go through it, and it cannot, this block cannot jump from the surface. So it moves only along the surface, and therefore the motion of the body in perpendicular direction has always zero velocity and zero acceleration in this direction. And therefore this force equals this force. That is n equals mg cosine alpha. Why? Because the block has no legs to jump. And the block and the surface is too strong, it cannot be broken by the block. The block moves only along the surface. That's why this formula is correct. So, in the direction of motion along this x-axis, where the acceleration is directed, we can find the acceleration, the mass of the body times acceleration will be the sum of all forces acting here. That will be r in magnitude minus f. We know what is r. That is mg sine alpha. And we know what is f, the force of friction. That is kmg cosine alpha. So mg is here, sine alpha minus k cosine alpha in round bracket. We have to find acceleration, so we divide by the mass, and the acceleration will finally be equal to g, the acceleration of free fall. The mass is cancelled, sine minus k cosine alpha. The coefficient of friction is some dimensionless number, just a number, just like 0.1, 0.2, 0.5. It may be equal to 1. It may be more than 1, more than unity. So it's just a number. For example, k may be equal to 0.5 in some particular case, something like that. It's just a coefficient without any dimension, without any units of measurement. So this formula was derived from the second Newton's law. And now look here. Suppose angle alpha is very small and it goes to 0. The surface is almost horizontal. Then alpha goes to 0, sine alpha also tends to 0, and cosine alpha will tend to unity. And then in this particular case, acceleration will tend to minus j, coefficient of friction. If this is 0, then the first term vanishes, and cosine tends to unity. Then what remains here? Only minus kg. And in this particular case, when the coefficient of friction is just 0.5, that will be equal to minus g divided by 2. It means that if the slope is almost absent, almost no slope, almost horizontal surface, then any object put on the surface, this one, should have this acceleration about 5 meters per second squared. Any object should immediately accelerate if it's on horizontal surface. But it's not so. We don't observe any acceleration. Any object is just at rest on the horizontal surface. But the formula provides some acceleration is necessary. Why is that so? Why is such a contradiction between the predictions of the formula and the observations? The formula predicts that if alpha goes to 0, if the slope is very small and the surface is almost horizontal, then the first term vanishes and the second term turns simply to k times unity. So the acceleration should be this one. But this is an absurd result, because we don't observe any acceleration when the body is at rest on the horizontal surface, or the surface which is almost horizontal. I may arrange for a small angle, small slope, but this doesn't accelerate. No acceleration at all. For small alpha close to 0, no acceleration, but the formula gives you an acceleration. Why so? Does it mean that the second Newton's law is incorrect? Or does it mean that we don't understand something here? That is the end of our lecture. So think about this problem, think about it at home. Is the second Newton's law incorrect, or we simply don't understand what's going on here in this particular problem? Think about it at home. Okay? So that's the end. Thank you all.